Welcome to the third and final part of Unit 7. In this part, we're going to work two more examples, both of which involve multiple objects. So, again, steps to solve these problems: draw a picture, determine what the problem is asking for, draw your free body diagram. If you need to, resolve any forces into components based upon the coordinate system you set up, and then you look at Newton's second law. And as needed, solve your equations simultaneously. The first example we're going to look at is a example out of rugby. So here we have a brave but inadequate rugby player being pushed backward by an opposing player who is exerting a force of 800 newtons on him. We are told the mass of the losing player plus his equipment is 90 kilograms and he's accelerating at 1.2 meters per second squared backward. We want to know the force of friction between the losing player's feet and the grass, and the force that the winning player exerts on the ground to move forward given his mass is 110 kilograms. So here we're dealing with two objects, and we need to draw the free body diagram for both because we want to know a force on either player for the answer here. So the first player I'm going to draw the free body diagram for is our brave fellow, even though he is not succeeding at our mission here. So there is the normal from the ground on him, and I'm going to call him player A. So the brave but inadequate player is player A. We have his weight. We have a force from the other player, who, as you might expect, is going to be player B, which I guess if the brave player B for brave, but that's not how I did it. And then we have friction between him and the ground. So there's his free body diagram, and this is one of the two answers we're looking for, and we're told that this is 800 newtons. On the other player, so the opposing player, who's going to be player B, he also has four forces on him. He has a normal force from the ground on him. He has his weight. There is a force from player A on him. And this one and that one are a third law force pair. So since this one equals 800 newtons, this one must as well. So how do we know they're a third law force pair? Well, they're the same type of interaction. They're both a contact force. They're between the same two objects, the two players, B and A. They're on two separate free body diagrams. They point in opposite directions. They've got all the hallmarks of a third law force pair. Therefore, they must be equal. Lastly, we have the normal from the ground on player B. And this is the other force that the problem is asking for. And one thing that I will say is I called it a normal force because it's a contact force, but this force has to have everything built into it. It also has to consider the friction between the player and the ground and all these pieces. It's all got to be buried into that. And we have a problem here because we have ground twice. So we use G for ground. Another letter. We'll go with S for sod. I don't know. It just needs to be something to distinguish it from the other force. Okay. The brave player is going to accelerate in the direction that he's being pushed by the other player. and the opposing player is going to accelerate in the direction that he is pushing on the ground. Right, so this would be backwards for this guy and forward for this guy. If I were to draw the picture, I'm not sure how helpful this actually is. And they should be touching, so we'll just extend an arm here. So this is my brave player, player A. This is the opposing player, player B, and they're both accelerating that way. Is what the picture would look like. Lastly, I'm going to define my coordinate system. I'm going to let x be in the direction of the acceleration and y be perpendicular to it vertically. Okay, so looking at our brave player first, the net force on our brave player, which was player A, is going to be the mass of player A times the acceleration, but since these guys are moving together, they have the same acceleration. Two forces on him. We have the normal from B on A, and we have the friction between him and the ground. And again, this is the number I want to know. So I'm going to solve for it. The friction between the ground and A will equal the mass of player A times acceleration. And if you look at the math there, that has to be negative. And plus the interaction force between the two players. So he had a 90 kilogram mass, if I remember correctly. He was accelerating at 1.2 meters per second squared, and the other force was 800 newtons. And if you multiply and add that all up, you get 692 newtons. On the opposing player, player B, F net on player B has to be the mass of B multiplied by his acceleration. We have two forces in the direction of the acceleration there. We have the normal from the sod and the normal from between the two players. The one from the sod is on in the direction of the acceleration, so we put it first. Subtract off the interaction between the two players. That has to equal his mass multiplied by acceleration. So the normal from the sod on B is going to be equal NAB plus mass of B times A, which is 800 newtons, plus 110 kilograms times 1.2 meters per second squared. And if you multiply and add, you get 932 newtons. And those are the two values that this problem is looking for. For the last example of this unit, we're going to consider a delivery by a drone. We have a 5 kilogram drone delivering a 0.5 kilogram package, which is hanging below the drone on a light cable. And we are told both objects, drone and package, are accelerating upward at 5 meters per second squared. We want to know the tension in the cable and the force from the air on the drone's blades, causing the drone and package to accelerate upward. Okay, so I mentioned in part 1 that I would be doing this particular example. And what I'm going to do is I'm going to work this example in two ways, showing that I get the same answer for the second question in both ways. Okay, the first way is I'm going to consider drone with its propellers. That's what these star things are. I guess they should be on arms so that they're actually connected with the package, everything accelerating upward. And I'm going to consider this as one unit. It's connected, why not? So in that case, I only have one free body diagram to draw. I have the force from the air on the drone and its blades, but we'll just use, let's use C for the combined drone package set, if you will. And we have gravity acting downward on that. I'm going to let the vertical direction be y and let that be positive upward. And if I apply Newton's second law on this, I get the force from the air on the combined system minus the combined system's weight has to equal the combined system's mass multiplied by the acceleration. FAC is what I want to know, so FAC will equal the combined mass times the acceleration plus, and now I'm going to rewrite the weight in terms of the combined mass times the acceleration due to gravity. So the combined mass is 5 kilograms plus 0.5 kilograms, so that's 5.5 kilograms. It's accelerating at 5 meters per second squared. And I add to that 5.5 kilograms times 9.8 meters per second squared. And that arrives at an answer of 81.4 newtons. And that answers the second part of the question. We now know what force the air has to put on the drone's blades to cause it and the package to accelerate upward. What we can't answer by viewing this system in this way is the first question. We can't identify the tension on the cable because the cable's just buried inside the drone package combined entity. So to find the tension of the cable, I have to I have to have another slide, and I thought I had one. I don't have one backwards. What I do have one is the other way, and when I post the slides, I'll put them in the proper order if you want to go look. Okay, so as I was saying, I need to look at the drone and the package as separate entities in order to get the tension. So on the drone, D for drone, I have force of air on drone minus the tension from the cable on the drone. I subtracted that because it's downward. The other thing I have acting here is the gravity acting downward on the drone. On the package, oh, that's a P. It doesn't look like a P. Let's try again, shall we? On the package, I only have two forces. I have a tension from the cable on the package pulling upward, and I have the package's weight pulling downward. Okay, we want to know the tension in the cable. What we do know is the acceleration is 5 meters per second upward. So let's begin by looking at the package. So the net force on the package will equal the mass of the package multiplied by its acceleration. Again, let's let positive be up because that's the direction of the acceleration. So tension of the cable on the package minus the package's weight. It's the mass of the package times the acceleration, or in other words, tension of the cable on the package is mass of the package times acceleration plus the mass of the package times the acceleration due to gravity. The package was 0.5 kilograms at 5 meters per second squared. There's a decimal place there. And I need to add to that 0.5 kilograms times 9.8 meters per second squared. And if I put all of that together, I get the tension in the cable is 7.4 newtons. Okay, problem solved. But what I wanted to do here as well was show that I can get the same answer for the force from the air on the drone as I got in the previous way of envisioning this. And this actually takes a little bit of extra work because on the package I have the tension in the cable on the package, And on the drone, I have the tension from the cable on the drone. And somehow I need to be able to equate those two things. To do that, what I'm going to do is I'm going to draw the free body diagram of the cable. So upward, I have the drone pulling it upward, and I have the package pulling it downward. Oh, and I wrote those two subscripts in the wrong order, so let's fix that. And now see, I have two sets of third law force pairs. I have the package and the cable, and the cable and the package, and I have the drone and the cable, and the cable and the drone. So now if I apply the Newton's second law to the cable, I get the net force on the cable is the mass of the cable times the acceleration. And I can rewrite that in terms of the forces. And here is where you might think that you're stuck, because nowhere in the problem statement did it say anything about the mass of the cable other than the fact that it is light. The fact that it is mentioned that it is light is actually one of those keywords in physics, which tells you that this is approximately 0 kilograms times 5 meters per second squared. It's not 0, but the mass of the cable is inconsequential compared to everything else going on in the problem, so approximated as 0. With that, that tells me that TDC equals TPC. And since I know TPC and TCP are third law force pairs, I can equate this like so. And I know that this is 7.4 newtons. And again, I have another set of third law force pairs up above. And I have successfully connected my two tensions to each other. Okay, I think maybe some lines separating the work on this problem might be a good idea. I hope I have enough room up above. So lastly, on the drone. Okay, we have one force in the direction of the acceleration, and that's the force from the air on the drone. We have two forces in the other direction, the drone's weight and that tension that we just did a lot of effort to find. Okay, so now I can solve for the force on the air from the air on the drone, and that will equal the mass of the drone times its acceleration plus the mass of the drone times the acceleration due to gravity. Remember, that's the weight force, plus the tension in the cable acting on the drone. Okay, so that's 5 kilograms times 5 meters per second squared, plus 5 kilograms times 9.8 meters per second squared, plus, and I'm going to get rid of that glitch, so plus 7.4 newtons. And if you multiply and add all of that together, you get 81.4 newtons, which is exactly the same number we got on the previous slide when we looked at it as just one combined unit, 81.4 newtons. This concludes Unit 7. In the next unit, we are going to be extending our knowledge of Newton's second laws by bringing in a model for friction that actually allows us to calculate friction forces.